I'd like to welcome you to the launch of our new public lecture series called Discover Psychology. And this lecture series, the goal of it is to be a bit different from typical research colloquium that we also host on Thursdays. These talks are meant to be delivering really accessible, engaging, interesting talks for a general audience that are based in science. So I guess I have a lot to live up to in the very first talk. Before we get started, I just want to thank a couple of groups that have been instrumental in helping to organize this series. One is the Alumni Office, and Laura Escalante is actually here representing the Alumni Office. They've been excellent in helping to promote and bring everything together and giving us their support. And also the Science Media Lab, who's doing all the recording. You may notice that these talks are being recorded. If you can't make one of these talks in person, you can always watch them online. They'll be available by the Tuesday at noon at iTunes University, the McMaster site. You can also access them by going to just discoverpsychology.ca. And on the Wednesday following each talk, there will be an interview online with the speaker, looking back at their talk. So if you're shy about asking questions in person, you can always join the discussion online and ask the really tough questions to the speaker in that form. And then we'll also post the transcripts for each of these talks. So it looks like we have a few people that just need to get some seats. Yeah. Maybe people at the edges can move in towards the middle to leave the seats at the end for latecomers. Wow, looks like we have a full house. So in my talk today, I'm going to be trying to answer a very basic question. Why should we approach psychology as a science? And normally at this stage of the talk, it's when the organizer would introduce the speaker and maybe tell an embarrassing story or two about it. In this case, I am both the organizer and the speaker, so I think I'll just introduce myself. My name is Dr. Joe Kim, and I'm the instructor for introductory psychology. And this is what I look like now. This is what I looked like when I was 6 years old. And this is what I looked like when I was 1. Embarrassing story about me is, any introductory psychology students in the audience, you may also recognize me from such web modules as Introduction to Psychology. Embarrassing thing about me is that I'm very poor at directions. And this is probably something I take after my mom. There she is. Who incidentally keeps a full record of all my report cards from grade school because you never know when you might need that. So I'm a psychologist, not that kind, and definitely not that kind, though I do have a couch in my office. My lab is interested in understanding how we can use technology to create effective teaching and learning. And those of you in the front rows may have noticed that I have quite a large head. And you know what they say about people with large heads? They have large brains. Which is, of course, a very good thing because, as you may know, we only use 10% of our brain. This is something that self-help authors and ad executives have known for decades. And apparently, so does most of the general public. In a 2002 survey, testing the general public's knowledge of neuroscience, although most people realize that emotions occur in your brain and not your heart, almost half the university-educated population believe this statement that we only use 10% of our brains to be true. So it begs the question, why do we start believing such ridiculous urban myths? If we start looking at this statement, we only use 10% of our brain, I'm not even sure what it exactly means. One possibility could be that the cells that make up our brain are called neurons. Maybe we only use 1 out of every 10 neurons in our brain. Or maybe we only use 10% of our brain and the other 90% is acting as some sort of cushion that protects the rest of the brain. However, we do know that damage to even a very small part of the brain can cause extreme damage and changes in behavior and personality. Case studies can confirm this. So the question then I want to answer in this lecture is, how do we come to evaluate new information? What sort of methods should we use? And I'll give you an example from my own childhood. My parents are of Korean descent, and I can tell you that as I grew up, I feared electric fan death. Some of you may not have heard of this before, but it is a very Korean-specific belief that if you fall asleep in a room with a fan running all night, you will surely die from hypothermia, or it could cause the air to flow past you. I recently confronted my parents about this about a few months ago as I was preparing another talk, and my mom assured me, oh yes, it is very dangerous. You cannot fall asleep with an electric fan on. And I did a little bit more research on this, and in fact, in the Korean media, there's about a story or two every summer reporting about someone dying from electric fan death. So, it's not just a Korean-specific phenomenon. Let's do a little bit of a quiz. I'm going to point out some statements to you. I'd like you to vote on whether you think these statements are true or false. So this will just give us a sense of where your own urban mythometer is at. So the first question is, the Great Wall of China is the only human-made object visible from space. Do you think that's true or false? Who thinks it's true? Raise your hand. Who thinks it's false? False is correct. It is just one of many things that you can see on Earth from space. In fact, the Great Wall of China is actually very difficult to see because it's made out of rocks from the environment that make it blend in. Second question. Older men have significantly larger ears than other subpopulations. Who thinks that this is true? Who thinks that this is false? It's actually true. There have been several longitudinal studies, I don't know why, that have documented that men have larger ears than women in general, and the older you get, older men have even larger ears. Third, your fingernails and hair continue to grow for up to 72 hours following death. Is that true? Who thinks it's true? And who thinks it's false? It's false. Once you die, everything stops. It is an illusion created by dehydration. Your skin pulls back, and it makes it look like your nails are growing. Fourth, the Coriolis effect influences water to spin down the drain in opposite directions in the northern and southern hemispheres. Is that true? Who says it's false? It's false. Water flows down the drain in the same direction everywhere in the world. It has nothing to do with the Coriolis effect. Finally, you're more likely to be helped by a crowd of people than by an individual. Who thinks that this is true? And who thinks that it's false? It's actually false. A crowd of people are a lot less likely to help you through a process called diffusion of responsibility. So if you shouldn't take my word for it. I would encourage you to look up references on your own, and here's some references to get you started. So the question then is, how do we know if something is true or false? I'm going to talk about 4 different techniques that you might use. One is we can appeal to authority. Secondly, you can use your own good common sense. Third, we can appeal to something refined like reasoning and logic. And fourth, we'll talk about the scientific method. And I'm going to draw on examples from across science in general and some questions in psychology in particular. But the same principles will apply across to all fields. So the first question, authority. It might be in my best interest to listen to my mother and eat all my vegetables and perhaps wait up to half an hour before I go swimming. But it begs the question, where did this woman get this knowledge? And can we even trust her? Because a statement that is unverified can lead to some very odd hypotheses. So in his great work, The History of Animals, Aristotle presented a long and apparently very convincing argument of why men and women should have different numbers of teeth. And so the educated class at the time believed that men have more teeth than women. No one bothered to check because this was such an elegant argument. But this is not something that is specific to just the general public. Even scientists can be fooled. Let me give you a brief history of cello scrotum. This is a debilitating condition suffered by cello players. Something to do, I guess, with the vibrations and the geometry of the placement of the cello in your lap. And it was first reported in 1974. And over the years, there were some questions on its authenticity, especially by Shapiro in 1991, who vehemently argued against the existence of cello scrotum. But then again, other researchers thought, yeah, it sounds about right. There was a paper as recent as 1997 talking about early stage inflammatory scrotal pseudotumor related to cello scrotum. Earlier this year, it was revealed that it was all a hoax. So the original authors reporting cello scrotum admitted and came clean that we just made it all up. It was all just a joke. And for decades, people had been citing this paper. So it's not just the general public that gets fooled. Scientists get fooled as well. So let's talk about common sense. Let's just throw taking advice from authority figures out the window. How about common sense? Well, the thing about common sense is that it gives you conflicting information. If I asked you, is it better if people are alike or not alike to be attracted to another? You might say birds of a feather flock together. Of course, that explains everything. Or what would be another common folkism that says the opposite? Opposites attract. So which one is it? You can use common sense to support any argument that you want. What's different about science is that we take these observations, we can come up with a theory, and then before the next observation, we can make some sort of prediction, a testable hypothesis, and then see what happens in the observation. So that is the power of science. In common sense, we only have after the fact or post hoc explanations, whereas in science, we can make really strong predictions. And I'll give you an example from psychology. There's a phenomenon called cognitive dissonance. Imagine I introduce you to an experiment. I bring you into the lab, and I ask you to do the world's most boringest task, whatever you can think of it. It could be just sorting through papers. And you do this for about an hour. And then I ask you, I really need your help. I know this was, I won't comment on the task, but I need you to tell the next subject that this is the most interesting study that you've ever taken, because I really need to fill out my experiment. And for your troubles, I'll give you either a $2 coupon to Tim Hortons or a $100 coupon to Tim Hortons. So here are the conditions. You do a boring task. I ask you to lie to the next person and tell them it's not boring. And I'm going to give you either $2 or $100. In the end, I'm going to ask you, you personally, come back, tell me, what did you really think of this study? How interesting was this study? Who is going to tell you that the study was more interesting? The person that you paid $2 or $100? Who else thinks it's $100? Who thinks it's $2? You'd be surprised that all the psychologists in the audience know that $2 will make you rate the study as being much more interesting. And the reason for that is that we're all good people. You're not going to lie, right? But if I paid you $100, that kind of explains why you lied, doesn't it? But if I only paid you $2 and yet you still agreed to lie, you obviously didn't do it for the $2, right? You must have done it because you actually believe it was interesting. So this is an example of a completely counterintuitive finding that you can't necessarily just explain with common sense. And it's a really powerful example from psychology. This might also help us to explain why we particularly value membership into an organization where there's a lot of hurdles for us to get through to. If you have to wait a long time to get into a specific club or a restaurant, there must be a reason. It must be so good, right? Okay, let me give you another example from geography on why common sense is not necessarily the way to go. This, of course, is a silhouette of the continent of Africa. Here's Africa on a very popular map used in North American classrooms called a Mercator projection map. So you can see the relationship between Africa and all the other continents. What may surprise you is that North Americans are very good at understanding the shape of continents, but they're very poor at estimating the relative size of continents. So you can tell right away from this graph that it's a bit skewed. It looks like Africa and South America are about the same size. It looks like Europe and South America here are about the same size. But of course, you know that South America is larger than Europe. The comparison I want to ask you is that Greenland looks about the same size as Africa, but I can tell you that Africa is larger. My question for you is, how many times larger is Africa relative to Greenland? Is it 2.5 times? Is it 4 times? 5 times? 7.5 times? Or 14 times larger? All right? Think about it for a second, and then we'll have a little bit of a vote. Who thinks that Africa is 2.5 times larger than Greenland? Okay. Who thinks it's 4 times? Who thinks it's 5 times? A bit more popular answer. Who thinks it's 7.5 times? And who thinks it's 14 times? It's actually 14 times larger. And most people are shocked to learn that Africa is 14 times larger than Greenland. And it's not surprising because you've never seen a map like this. This is called a Peters projection map, which accurately portrays the total surface area of a continent. And you can see here that Africa is, well, it doesn't show up very well here, much larger than Greenland. What this map doesn't show you is the proper shape of the continents. That was sacrificed to make this type of map. So one point I want to make here is that a map is really just a model of the three-dimensional world that we live in. And models have limitations. Models can also influence how you perceive the rest of the data. So for example, if all you knew about the world was from a Mercator projection map, you'd have an accurate understanding of the shapes of continents, but you would not have an accurate idea of the relative sizes of the continents. Now, if all you knew about the world was from a Peters projection map, you'd have an accurate idea of the relative size of continents, but you would not have an accurate idea of the actual shapes of the continents. Now, if all you knew about the world was from these two types of maps, you might assume that this is the top of the world. But that's just another convention of the map maker. This is a Hobo-Dyer projection map, which may look funny to some of you because it looks like an upside-down world. But seen from space, this is just as legitimate a map as any other map. Now, if all you knew about the world was from these types of maps, you might not realize that McMaster University is the center of the universe. And this map is just as legitimate as any of the other maps that I've shown you. So a couple points I want to make here is that flat maps are just models that represent a three-dimensional Earth, and they have limitations. Secondly, they can influence how you perceive the world. If you've only seen one type of model, that's probably going to influence how you see the entire data set. Okay, so maybe we won't use common sense. Let's move on to reasoning and logic. So reasoning logic works something like this. If A and B are true, then C must also be true. And there are those who are strong proponents of logic, and there are those who think it could lead you astray. And I'll give you an example that I first talked about when George Bush was president, but I still think it has some relevance. I'll give you an example where we could distinguish between truth and logic. So example 1, statement A says that all presidents are warm-blooded. Statement B, George W. Bush is president. Therefore, George W. Bush is warm-blooded. Turns out that statement A is true, statement B is true, and the conclusion reached in statement C is also true. This is a valid argument. But I'll give you another example. A, all Yale graduates are warm-blooded. George W. Bush is warm-blooded. Therefore, George W. Bush is a Yale graduate. In this case, statement A is true, statement B is true, and the conclusion reached in statement C is true, but it's actually an invalid argument. This conclusion does not follow from the first two statements. And finally, all presidents are elected by winning the popular vote. George W. Bush was democratically elected president. Therefore, George W. Bush was democratically elected president by winning the popular vote. In this case, none of these statements are true, but it is a valid argument. So there's a distinction that we have to make between truth and logical validity. And one problem with logic is that we still don't know what is true. We have to start off with at least one statement that's true before we can move on. Okay, Obviously, the scientific method is the way to go. And there's a few rules of engagement that scientists use to make sure that they make sound conclusions. One is called parsimony. And this idea is that all things being equal, we're going to take the simplest explanation that best explains the data. No need to get complicated. We'll start off very simple, and if that explains everything, it's fine. Secondly, scientists are quite conservative. We don't jump to crazy conclusions. In the newspapers, you read about studies all the time that could change your life overnight. Scientists typically are very skeptical about these things, and they'll have to see the data. Third is generalizability. We work in a university, we work in labs, we collect data, but our assumption is that what we're finding here in our labs and our reports and journal articles will eventually lead to results that can be generalized to applications in the public. Some of these things we might not even realize yet, and these are things that we're working on, but we assume that what we learn here also applies in the real world outside the university. So I talked a bit about how science is different from common sense. The power is that after seeing a series of observations, we could form a theory and then develop specific testable hypotheses that can lead to really interesting results. And I just want to tell you about one of these. This is a study from Jeff Norman's group at McMaster University. Imagine that I have some nursing students, and I want to teach them about the relationships between the bones in your hand. And there might be a couple different ways that we do this. One might be I could just show the students classic diagrams where they're just two-dimensional diagrams, front and back, that show all the bones. And that could be the old way to do it. I could present another group of students where I present them with a high-tech solution where there's a 3D animating hand. And it shows all the relationships of the bones, but in real time and space, and you can see their relationship with another that way. If you test them, many people might assume that, of course, this high-tech solution must lead to better understanding of the relationship between the bones and the hand. But in fact, we find the opposite, especially if a person does not have direct control of the speed at which the hand rotates. It's actually very taxing on their attentional and cognitive systems. And it leads to worse performance on a test when nursing students are actually asked to talk about the relationship between bones and the hand. And this is an experiment. This is a result that would only be known to us if we actually run an experiment. So another plus for scientific method. I'll tell you about one other interesting story that I came across. It's a story of Warren and Marshall, who were awarded the Nobel Prize in Medicine just a few years ago. They did research on the cause of peptic ulcers. And the prevailing hypothesis at the time was that ulcers were caused by a combination of stress and diet. And this idea became so well ingrained that many scientists believe that there could be no other possibility to causing ulcers. But they found some weird things in the data. One observation that they did make was that not all patients had this combination of stress and diet that could lead to ulcers. But when they looked carefully at samples from biopsies, they found that there seemed to be this bacteria called H. pylori that was present in a lot of these patients. So at this point, it was just sort of a coincidence. But if they looked back at the data and they looked hard enough, they found that, sure enough, almost every patient that they looked really carefully, they could find this H. pylori. So they published these results, and scientists were very skeptical because scientists are very conservative, and rightfully so. No one believed that this could be true. And in part, they thought that we already have our specific set of beliefs. It became what we call dogma. And people thought there could be no other possible explanation. So their papers were actually rejected from a lot of the top journals. Until one day, Marshall was frustrated and he thought, I'm going to prove this. I don't want just correlation. So he consumed the bacteria himself. He documented the ensuing ulcer that formed. And then he treated himself by giving antibiotics that killed the bacteria and got rid of his ulcer. And today, we don't treat ulcers but as a combination of stress and diet. And you can imagine there was a huge pharmaceutical backdrop to all this as well. If you had an agent that dealt with by drug therapy this way and it's wrong, there's a huge political cost to that as well. So lessons from ulcers is that some ideas become so well entrenched, even for scientists, that it's really hard to see beyond that and accept new ideas. And often, a very simple hypothesis best explains the data. And that was certainly true in this case. And correlation, though powerful, is not the same thing as causation. Correlation is just a relationship between two stimuli, but it doesn't say that one directly causes the other. I'm not suggesting that you do this, but he took the matters into his own hand, and he directly caused the ulcer to form, which can lead you to make a very strong conclusion. So a famous Swiss patent office clerk once said that all our science measured against reality is primitive and childlike, and yet it's the most precious thing that we have. So that is the role of science in our society today, to help us answer these questions. And scientists are very conservative. They don't necessarily go out to prove things, but they try to eliminate false hypotheses. And that's best summarized by this quote that I found from Bertolt Brecht, who's actually a poet. He said that the aim of science is not to open the door to infinite wisdom, but to set a limit to infinite error. And that is what scientists do. So to sum up so far what I talked about, I started off by telling you some modern-day myths and truths. So let's recap. You definitely use more than 10% of your brain. Older men have larger ears than anybody else. The water flows down the drain in the same direction here and here, though Bart Simpson may disagree if you watch The Simpsons. The Great Wall of China is just one of many things you can see on Earth from space. Your fingernails and hair definitely stop growing after you die. You can't necessarily take the word of an authority figure at face value, even if it is your mother. Common sense and logic can fail you. Scientific method provides us with something that's very objective and gives a very systematic way of looking at the data. Even then, you should be a healthy skeptic. So I want to ask you one final question. Some of you may have read about 12/21/12, December 21st, 2012, which may or may not be the end of the world. And I want to ask you a couple of true and false questions and just tell me what you think. First of all, is it true that on December 21st, 2012, the Mayan long count calendar will mark the end of its 5,126-year era? Is that true or false? Who thinks it's true? False? Commit yourself. Okay, it's actually true. Okay, second point. On December 21st, 2012, the Earth, the Sun, and the center of the Milky Way galaxy will be in alignment. Is that true or is that false? Who thinks it's true? Who thinks it's false? It's actually true. Point 3. Points 1 and 2 together will lead the Earth to tilt off its axis and end life as we know it. Is that true or false? Who thinks it's true? Okay, a few people, a few believers. Anyone think it's false? Okay, I got through to some people. That's good. In fact, there's a movie coming out this November called 2012 that capitalizes on all this hype, and they have a brilliant ad campaign. They tell you to Google search 2012. Because when you do that, you come up with I did that last night, and almost every website gives you misinformation about 2012, particularly how the world will end in 2012, say experts. So it is true that the Mayan calendar does end its 5th era at 5,126 years. That's true. And if you check the star charts, it's also true that the Earth, the Sun, and the center of the Milky Way will be in alignment. What they neglect to tell you is that this happens every year. Every winter solstice, on December 21st, 2012, the Earth, the Sun, and the center of the Milky Way are in alignment. So there's actually nothing special about this. But if you go on the internet and you read any of these sites, you could become convinced that maybe you should make some plans for December 1st, 21st, 2012. And I think that's all I have to say today, actually. I have a very short talk that I just wanted to set up the rest of the talks, give you a preview of what's to come. The talks that we're going to be having in this series very much focus on science that's very accessible to you, the general public. The next week's talk will be Stephen Brown. Right here, he'll be talking about, his talk is called Tango in the Brain, the Neural Basis of Dance. He is in our Department of Psychology, Neuroscience, and Behavior. He's also appointed in the McMaster Institute for Mind and Music, and it should be a very fascinating talk, and I hope you can come out. And in the meantime, I'd be happy to take any questions. Any questions?